Mathematical Methods by S.M. Yusuf, Abdul Majid, and Muhammad Amin. This book is for the BSc students, and we are going to start exercise 8.1 of this book, Mathematical Methods. This exercise is basically for the infinite series, that we have to check whether the nth terms of these sequences converges or diverges. For that purpose, you must know that what converges and diverges means. If you apply the limit on some nth function, like you see here in the questions, you are given with some nth terms of the sequences. If you apply the limit n approaches to infinity, if it is depending upon n, then n approaches to infinity. If it is depending upon x, then x approaches to infinity. So if we apply the limit on the nth term of a sequence and it give us some definite number, then it means that the series converges. But if after applying the limit you don't get a definite number in your answer of the limit, then it means your series diverges. For example, here it is given that the divergent sequence is a sequence that does not have a definite number, as its limit is said to diverge or a divergent sequence. So if you apply a limit on the nth term and you get not a definite number in your answer, like you get infinity or the undefined answer, then it means it is a divergent sequence. But if you get some 0, 1, 2, 3, any defined number in after applying the limit, then it means you have a convergent sequence. So starting from this question number 1, that is, the nth term of a sequence is given, determine whether the sequence converges or diverges. If it converges, find its limit. So starting from the 1, apply the limit on this nth term, limit n approaches to infinity, 2 over under root n square plus 3. Now here in this exercise, your limits techniques are used here. So you must be good in applying the limits. We know that if the limit is on infinity, like you have to put the infinity, so we can just make the terms in fractions form of the n. Like we can just take the n common out of it. So it will become limit n approaches to infinity, 2 over, if we just take n out of it common, we can just take n square common inside, and after coming outside this under root, it will become n. Like you see here, if we have here n square plus 3, inside take n square common, we'll get 1 plus 3 over n square. Now we can take this n square out and it will be written as n, and we will be left behind 1 plus 3 over n square. If we apply this limit n approaches to infinity here, this will be 3 over infinity will become 0. So 1 plus 0 under root will give you 1. So this term will be just finished because it is 1 here. Then 2 over infinity will give you the 0 in your answer, like this. So this is a defined answer. So you will say like the sequence converges to 0. So this is the answer of your limit, because the sequence is convergent and its limit answer is 0 here. Question number 2. N minus 3 factorial over n minus 1 factorial. This is the sign for factorial, and you know that how to open the factorials. For example, you have n factorial, you can just open it like n minus 1 into n minus 2 into n minus 3 and up to so on. If you just finish it here, you will write it like n minus 3 factorial. It means it is just continuing. You just keep subtracting 1 out of the each bracket if you are moving on the right side. Here we have, just apply the limit on it, limit n approaches to infinity, n minus 3 factorial over n minus 1 factorial. It can be written as limit n approaches to infinity. I can open this n minus 1 factorial if I keep subtracting 1 out of it. At one point, I will get n minus 3 here. So that n minus 3 can be cancelled with this n minus 3. So I need to open this one. So it will be n minus 3 factorial divided by. Now keep moving on the right side. It will be n minus 1 into n minus 2 into n minus 3 factorial like this. I stopped here, so I will write factorial with it. Now this factorial and this factorial will be cancelled with each other. So we will get limit n approaches to infinity 1 over n minus 1 into n minus 2 here. Now we know that if we just replace n with infinity, so 1 over infinity will give you the 0 in your answer. This is a defined answer. So our sequence converges and the limit is equals to 0. The sequence converges and its limit is 0. Now come to the question number 3. 1 plus minus 1 over n over n. Apply the limit. Limit n approaches to infinity 1 plus minus 1 raised to power n over n. We know that this is a general formula that if we have limit n approaches to infinity on minus 1 raised to power n over n, that will be always equals to 0. This is the general formula. You can use it here. Apply the limit on 1 and apply the limit on this function. You will get 1 plus 0. This is equals to 1. So the sequence converges and its limit is 1. Question number 3. We just did question number 3. We are on question number 4. Under root n plus 1 over n. Limit n approaches to infinity on under root n plus 1 over n. This can be equals to, if I just directly apply infinity here, it will become infinity by infinity form. So I just need to rearrange the terms. I can take n common, that will be 1 plus 1 over n divided by n. Now I can separately divide this under root into these two terms because both are in multiplication form. It can be written like under root n into under root 1 plus 1 over n. And you know that this denominator can be broken as under root n into under root n. So this will be cancelled and we will get 1 plus 1 over n under root n like this. If I just replace the terms, we have here limit as well. Limit n approaches to infinity, limit n approaches to infinity here, and limit n approaches to infinity also here. If we just apply infinity here, this will be 1 over infinity and that is goes to 0. So 1 plus 0 will give you some defined answer like 1, and this 1 over this infinity, this 1 over this infinity will give you answer as 0. So I got 0 in my answer. So the sequence converges. The sequence converges and its limit is 0. Question number 5. In question number 5, you have n raised to power 1 over n. Let this n raised to power 1 over n equals to y. Because we cannot directly put the limit in this will be difficult for us to solve. So just let it equals to y. We know that we can just take these powers down if we have some log function here. So applying natural logarithm on both sides, I will get ln y equals to ln n raised to power 1 over n. Now this is a property of log that this power can be come down in the coefficient of ln. So it can be ln y is equals to 1 over n ln n like this. Now this can be written as ln n over n. This is ln and this n is, don't just get confused with these two n's. Now we need to know this limit. Just applying the limit on both sides, limit n approaches to infinity ln y equals to limit n approaches to infinity ln n over n. We cannot directly put limit in this because it will give just some undefined indeterminate form or undefined terms. You can use the L'Hopital rule here. Limit n approaches to infinity. Using the L'Hopital rule here, take the derivative of numerator and take the derivative of denominator separately. The derivative of numerator will give you 1 over n and the derivative of denominator will give you 1. It will become limit n approaches to infinity 1 over n like this. Now you can put the limit here. 1 over infinity will give you the answer 0. So we got 0 here. So our equation is reduced into limit n approaches to infinity ln y equals to 0. Now in our question we had y, not ln y. So we need to remove ln out of here. So we know that we can remove this ln by taking the exponential. So taking the exponential on both sides, we'll get limit n approaches to infinity e raised to power ln y, that is equals to e raised to power 0. This can be cancelled and we get limit n approaches to infinity y equals to 1. And this y was limit n approaches to infinity n raised to power 1 over n is equals to 1. So the sequence converges and the answer of this limit is 1. Now come to question number 6. In question number 6 you have 2 raised to power n over 2n factorial here. In the questions in which we have in the numerator the power function, in which we have that main variable in the power, and in the denominator we also have that main variable. In these kind of fractions and the powers, the ratio test is the best test that decides whether the sequence converges or not, and that will give you the best answer of your limit easily. That is the easiest method to check whether the sequence converges and what is the answer of that limit, the ratio test. And the ratio test is here in your book. It is on page number 349 after the exercise 8.2. The ratio test is given here. In the ratio test, you basically need your an function, that is your this function, main function. This is let it equals to an, and take an plus 1 out of that. Replace n with n plus 1 and then take its ratio like an plus 1 over an and apply the limit and get the answer. If this answer L is less than 1, then it means your sequence or the series is converging and the answer will be that limit L. If it is greater than 1, then it is diverges, and if it is equals to 1, then the test fails. So I will just use that test here. Your an here is 2 raised to power n over 2n factorial. An plus 1 will be equals to 2 raised to power n plus 1 over 2 into n plus 1 and this factorial. So it will be equals to 2 raised to power n plus 1 over 2n plus 2 factorial. Now an plus 1 over an equals to this thing, 2n plus 1 divided by 2n plus 2 factorial. Now this main division sign I am writing it with this sign and divide it with an, so division an, 2n over 2n factorial. 2n plus 1 divided by 2n plus 2 factorial, take its reciprocal and change this sign into the multiplication, will get 2n factorial over 2 raised to power n. Now we know that this thing can be written as 2n plus 1 can be written as 2 raised to power n into 2. So 1 2 raised to power n and 1 2 raised to power n can be cancelled with each other. So we'll get 2 over 2n plus 2 factorial. This 2n plus 2 factorial can be written as 2n plus 2 into 2n plus 1 into 2n factorial. I just moved 1 unit on the right side. Just subtract 1, I will get the main function 2n plus 2. Then subtract 1, I will get 2n plus 1. And then subtract more 1, I will get 2n factorial. And here I have 2n factorial over 1. This will be cancelled. So I will be left behind 2 over 2n plus 2 into 2n plus 1, like this. Now I can take 2 out of common here. So I will get an plus 1 over an equals 1 over n plus 1 into 2n plus 1. Now apply the limit n approaches to infinity, an plus 1 over an. That will be equals to, you see here we have infinity in the denominator. So 1 over infinity will give you 0. And you know that 0 is less than 1. So it means the series converges, this one. The sequence converges and the answer of this limit is 0 here. Now question number 7. 3n raised to power 4 plus 1 over 4n square minus 1 here. Limit n approaches to infinity, 3n raised to power 4 plus 1 divided by 4n square minus 1 here. I can take n4 common out of here. So limit n approaches to infinity, n4, I will left behind 3 plus 1 over n4 divided by, take n square common. If I take n4 common so that I can cancel it with this n4. n4 common, I will get here 4 over n square minus 1 over n4 like this. It can be cancelled now. So I will be left behind limit n approaches to infinity, 3 plus 1 over n4 over 4 over n square minus 1 over n4. Now, it will be 3 plus 1 over infinity will give you 0. So 3 plus 0 over will get 4 over infinity. 4 over infinity is 0 minus 0. So you see here we get 3 over 0 here. This is undefined. So the sequence converges here. And we cannot get the answer for its diverges. It is diverges because we haven't got some defined answer here. The sequence diverges, so that we have no answer for its limit in this question number 7.